For a long time, URP Shader Graph didn't officially support post-processing, and you were forced to write code-based renderer features instead. But thankfully, Unity added the full-screen material type in Unity 2022. In this tutorial, we're going to learn how this graph type works and create a couple of effects, namely a grayscale color filter and an edge detection outline effect. I'm working in Unity 6.0, but the workflow for any version from Unity 2022.3 onward should look similar to this tutorial. To start off, post-processing just means any technique that modifies the screen after you've finished normal rendering. That includes any of URP's built-in effects like bloom, vignette, or tone mapping. When creating these effects, we have a limited amount of data to work with. Namely, we can access the colors in the screen texture, the normal vector, and depth of each pixel on the screen, and, if we're using them, the motion vectors. Post-processing is the final step that you can use to elevate your game's visuals and get a more pleasing color balance, or maybe introduce stylistic elements that might be difficult without post-processing, such as outlines. Or maybe you're making Twilight Princess and you just really want to crank up that bloom to 11. Speaking of post-processing, I just released Snapshot Shaders 2, a revamped and improved pack of post-process effects for URP. The core feature is that every effect in the pack can be masked out and applied to only specific object layers. And there's a ton of filters such as height-based fog, silhouette, painting, retro, blur, and more. There's still a 50% launch discount for a few more days, so I'd love if you could check it out. Let's get started creating a grayscale filter, which will turn each pixel a different gray based on its luminance, which is also called brightness. Right-click in the project view and go to Create Shader Graph, URP Fullscreen Shader Graph, and name it Grayscale. Open it up and the graph will look like any other, except over in the graph settings you will find slightly different options to usual. We won't really be touching these in this tutorial. On the main graph surface, let's add a node called URP Sample Buffer. This node is used to retrieve those screen textures I mentioned earlier. At the bottom of the node, there is a source dropdown, and we can cycle between the normal vector in world space, the motion vectors, and something called blitz source, which is just the color. We'll be using that last one, blitz source. Unfortunately, the preview window on this node doesn't really give us any useful information, so we'll be working largely in the dark when creating full screen graphs. You may be wondering how to get depth information, and we can use the existing scene depth node for that, which you may find useful for creating some effects. It's also worth noting that you can technically use the scene color node here too, but that's a separate texture which is set once before post-processing starts, so you won't be able to chain the output from one post-process to another if you use it. A grayscale filter is extremely simple. We just need to weight each of the red, green, and blue color channels of the screen color based on how sensitive the human eye is to those colors, and condense them into one value. We can do that by taking the dot product between the screen color and a vector of those weights, which are 0.212 for red, 0.715 for green, and 0.072 for blue. Then we can output this value to the base color graph output, and we are done with the shader. Let's save it and return to the scene view. To use this grayscale filter, first create a new material which uses this shader. Then we need to find our URP renderer data asset, which is probably inside the settings folder if you're working from a fresh URP project. Let's select the PC_renderer and then click Add Renderer feature at the bottom and choose Full Screen Pass. By default, you'll see this kind of ugly color invert filter, but we can replace the material with the one that we just created, and our grayscale filter will appear in both the scene and game views. Awesome. For completeness, I like to make sure that color is selected in the requirements field, although I'm unsure if you need to do that. And we can rename the effect to grayscale here, so it's easier to keep track of it if we use multiple effects. The grayscale effect was very simple, so let's jump in with something a bit more complicated. To draw outlines over our scene, we need to detect edges somehow, and we're going to do it by finding changes in color by taking gradients across different pixels in the image. Essentially, for each pixel in the image, we will find the difference in color between the pixel above, below, to the left, and to the right. Let's create another graph via Create Shader Graph, URP Fullscreen Shader Graph, and name it Outline. On the graph, we'll start right at the end. We're going to take the original screen texture and overlay the outlines onto it. So to start, we'll add a URP sample buffer and feed its output to a lerp node's A slot. Then we can add a color property named Outline Color and drag it onto the graph into the B slot. The T slot is going to be a value between 0 and 1, where 0 means there's no outline and 1 represents pixels where there is one. We can feed the lerp output to base color. Next, let's leave a lot of space to the left and start to build up the nodes that detect edges. First, we will set up the UV offsets for sampling the screen texture. Start with a screen node, which gives us the width and height of the screen in pixels, then take the reciprocal of both to give us the UV offset for sampling one pixel to the right and above in the X and Y directions. We can use vector2 nodes with these values to set up both offset vectors. Next, we need to create vectors for sampling down and to the left by negating both of those vectors. So overall, we should have 4 offset vectors to sample left, right, down, and up respectively. These offset vectors need to be applied to the screen space UVs, which we can get with the screen position node. And then we can set up 4 tiling and offset nodes with the screen position in the UV slots and our 4 offset vectors plugged into each one. To recap, from top to bottom, we now have a set of UVs to sample the pixel to the left, right, down, and up from the center pixel currently being drawn. From each tiling and offset node, let's wire up a new URP sample buffer node, making sure that the blitz source mode is used on each one to sample screen colors. The next step is to find a gradient across these 4 samples. We do that cheaply by finding the magnitude of the difference in both the X and Y directions, adding them together, and applying some threshold value so that if the difference is high enough, we register this pixel as an edge. So let's do just that. Take the top 2 nodes and subtract one value from the other, and then do the same for the other 2 nodes. This gives us 2 vector values, but here's a neat trick. If you take the dot product of a vector with itself, you get its squared magnitude. So I'll do that to both vectors so that we have 2 float values, where each one gets larger if the color difference is stronger. You could take the square root of each, but it's cheaper if we don't, and the effect will still work. So let's add the 2 values together, and now we need to apply a threshold value. We can add a float property called color threshold and set its mode to slider so that it only accepts values between 0 and 1, and then use a step node with the threshold in the edge slot. This step node gives us a binary value where 1 means an edge has been detected, where the difference in color exceeds the threshold value, and 0 means we should use the original screen color. We can output this value to the T slot on the lerp node we added at the start, and now we have a shader which detects edges based on color gradients. If we create a material using this shader, and then add a second full screen pass to the renderer features list, then if we tweak the color threshold on the material, we will see the outlines getting stronger or weaker. Plus, we can change the outline color to whatever we want. We can go one step further with the shader. Detecting color-based gradients is all well and good, but we have access to normal information via URP sample buffer, so let's use it. First, we'll use a distinct threshold for this, so that we can configure the color-based and normal-based edge detection separately. So add a float property called normal threshold, and this time it should be a slider between, say, 0 and 5. Next, let's set up the normal-based edge detection nodes. Most of the nodes are identical to the color-based detection, so we can just copy them. Drag a box around all the nodes, starting from the 4 URP sample buffer nodes to the step node, and copy them all, and then drag the copies down below. For each of the URP sample buffer nodes, let's change their source to normal world space. Then swap out the threshold value for the new normal threshold that we just created. This set of nodes will detect differences in normal vector of each pixel. So if we have an object with similar colors, but a distinct edge on its mesh, we can detect those. Finally, let's add our color edge detector from before to our new normal edge detector and feed that value into the lerp node T slot instead. Now, if we save the graph and return to the scene view once more, we can tweak the normal threshold and see even more edges. For peace of mind, I also make sure that the full screen pass has the normal selected in its requirements section. The full screen graph type is a rabbit hole of its own. I encourage you to have a play around with it. Try tweaking the screen view v's input to the URP sample buffer node, or maybe overlaying your own textures and colors to the screen in weird ways. There are plenty of things you can do with it, so perhaps I'll cover more of these in the series in the future. Until next time, have fun making shaders.